So welcome back all the participants to the third lecture of the first day of the webinar on the standard model and beyond. So I welcome Dr. Rishi Khatri from TIFR Mumbai for the third lecture with entitled Fundamental Physics with Cosmic Microwave Background, Lambda CDM Anomalies, New Particles and Primordial Black Holes. The talk is all about the Lambda CDM model and beyond. So I am just reading through the abstract. The beginning of modern cosmology can be traced back to the great debate in 1920 between two astronomers, Kepler and Curtis, about how big the universe really is, and in particular, if the Milky Way is the whole universe. We have made great progress in the last 100 years, starting with the discovery that the universe is expanding and culminating in the establishment of the standard model of cosmology, which is known as Lambda CDM model. I will explain the standard model and the important role of the cosmic microwave background, the oldest photons in the universe, in making cosmology a precision science. I will also talk about how, as the experimental precision improves, looking for anomalies or deviations from the standard model with the future cosmological experiments can lead us to discover new fundamental physics and new particles and interactions beyond the standard model of particle physics. So, Dr. Khatri, he is a faculty in TIFR since 2015. Before that, he did his postdoctoral fellowship from Max Planck Institution for Astrophysics, Garching. And before that, he did his PhD from the University of Illinois in 2010. So he is the youngest of our guest speakers for this event. So without wasting time, I would like to request Dr. Khatri to start. And on behalf of the organizers, I would like to thank him very much for accepting the invitation with a single mail. So he just agreed readily. I'm so thankful that you spared your time to share and to tell the people that how cosmology is related to particle physics, how cosmos can be a big laboratory for testing the particle physics theories. And I really welcome you to the session. Please, over to Dr. Khatri.
Thank you. Yeah, so as Atri already mentioned, what I am going to talk about. So again, so this is a lot of material. We have to cover the 100 years of cosmology. So I don't know how much I will be able to cover. So let me just give you some essence of what you should try to take away from this. So I hope that you all have heard about what cosmic microwave background is. It is the earliest light, the ancient light that fills our universe. And the observations of this cosmic microwave background, so it's cosmic because it fills the universe. It's microwave because today we observe them in microwave frequencies, but as we will see that earlier on it was actually much higher frequencies or much shorter wavelength. As we go go back in time. And it's a background. So it is a background because this is the oldest light. So it is, so any object that we see, this CMB is actually behind that object. So it is a background, it forms background for the for our observable universe, at least in the electromagnetic waves. So no photons come to us that are beyond the CMB. So CMB is basically, these are the furthest photons that we can see. Anything else that we see, it is in front of the CMB. There's a cosmic microwave background. And what I have shown in this main slide, there are two parts to the slide. So this cosmic microwave background is actually a very almost perfect black body. It is not a perfect black body, you have to keep in mind, but it is almost perfect black body radiation. So you've all seen, I think you all know what a black body spectrum is. You have seen it in your elementary physics classes. So if you just look at the black body part of the spectrum, then what you see, the picture on the left side, So you can see my pointer also, yes?
The pointer is visible.
Yes.
Pointer is
So
visible.
the left-hand side is the black body part of the CMB. So if you just measure the black body part of the CMB, and what I have plotted here is deviation from the average. So CMB has average temperature of 2.725 Kelvin. So it is a very, very cold radiation. If you look at, we can actually measure now the temperature at microkelvin precision level. If you look at the very precise measurements, if you remove this 2.725 average, what I have shown here is the deviation from this average. So these blue spots, they are slightly colder than temperature is hundreds of microkelvin less than 2.725 Kelvin. The red spots are points in the sky where the temperature of CMB is slightly hotter or slightly more than about 100 microkelvins more than 2.725 Kelvin. We see that this temperature is actually not uniform, the picture, but there are these small fluctuations. And there are a lot of information in these small fluctuations. Just like if you have any field in 3 dimensions, you have any functions of space, right, f of x, you can take a Fourier transform. So here we have a function which is on a sphere. So we see this CMB at different directions in the sky. So these points, so this is basically a sphere that I have folded out. So each point is at a particular theta and phi direction in spherical polar coordinates. So spherical polar coordinates, the equivalent of a Fourier transform is a spherical harmonic transform. If you do a spherical harmonic transform and then you square that, you get the power spectrum, and that is what is plotted here. So this L is like the Fourier wave mode K in flat space, but on a sphere, we talk about L, which is the Fourier counterpart of the angle. So L is like 1 over theta, just like K Fourier mode is 1 over lambda. So what I plotted here is the this power spectrum of this. So I have condensed this information in this picture into a power spectrum. This power spectrum has very peculiar features. It has these peaks and dips, and they happen periodically. And there's a lot of information about the heights of these peaks, the relative heights, and in the whole spectrum, the whole shape of this spectrum. And when we measure this we can measure this now actually very, very precisely. The latest experiment to measure this, or this Planck experiment by European Space Agency. And it turns out this is very sensitive to what the universe is made of. How much matter there is, how much dark matter there is. Basically, the dark matter are particles which are not in the standard model of particle physics. How much baryons there are. Baryons means protons, neutrons, and electrons, or atoms, ions, protons, neutrons, and electrons. So how many baryons there are. How much dark energy there is. It is sensitive to if there is dark energy or not. Whether the universe is flat or not, what were the initial conditions of the universe, all that information is encoded in this power spectrum. And you see many, many lines here. And if you change all of these parameters, if you put a little bit more dark matter than baryons, these features change. And that is what is showing here. So in each of these features, I have basically changed some parameter. I have changed expansion rate or the baryon density or the dark matter density, and this changes. So by measuring this very, very precisely, we can know a lot about the universe. On the right-hand side, what I have plotted is the part of the CMB that is not a black body. So if you subtract out the black body part, you fit the best possible black body part spectrum to the observed CMB, and you subtract that out, what is left is a deviation from a black body. And that is what is shown in the right side. And this is actually a map of what we know called Sonev-Zeldovich effect. So what this is, what happened is that, as I told you, that CMB is the background. It is behind everything. And as the CMB is traveling to us from very far, very early universe until it is passing through all the structures that is between us and the CMB. So the surface from which the CMB is coming, which is called last scattering surface. So you will hear this phrase a lot, last scattering surface. That is the surface which we are seeing in CMB. Just like when you look at a wall, right? The fact that you are able to see a wall of your room is because photons are coming from wall straight to you. But you cannot see behind the wall because the wall blocks the photons which are coming from behind the wall or which are even inside the wall. Right. So what we are seeing when we look at a ball are the photons which last scatter from the ball and then they are coming to us. So photons which are being reflected from the ball. The same way CMB is also, we are seeing what we see is basically photons which last interacted with plasma, the primordial plasma of electrons and ions. And after that, they are coming straight to us. So what we see, the last scattering surface is like a wall in the early universe from which these CMB photons are coming to us. Before that, the photons are scattering with the matter particles. So we cannot see behind that wall. Right. So the CMB, as it is coming from this last scattering surface towards us, it is passing these clusters of galaxies. So clusters of galaxies are basically ensembles of galaxies which are bound together by their own gravity. And in between the galaxies, there is very hot gas. This gas is fully ionized, and it has temperatures of about 10 million to 100 million degrees, or in keV, this is about 1 keV to 10 keV temperatures. And there's free electrons, so electrons, these very hot electrons. The CMB scatters on these electrons by the photons and the electrons scatter with each other. This process is called Compton scattering or Thomson scattering. And because in this is elastic scattering, so if you remember your elastic scattering from, you heard it to a 12th class, if you have two particles which collide and which has one particle has much higher energy than the other particle, then there will be energy transfer from high energy particle to the low energy particle. And that's what happens here also when CMB collides with these cluster electrons in cluster, the electrons transfer some energy to the CMB. So CMB becomes slightly hotter. So I have plotted in this plot, what it shows is basically a deviation from a black body spectrum. So some photons which were at the low energy, so at 100 gigahertz or less than 100 gigahertz, they have been upscattered, they have gained energy, and they have become to frequencies which are higher than. So just look at the black line here. So photons which were below 100 gigahertz, they have become more than 100 gigahertz. So you have photons taken some low energy photons and moved them to high energies. So do you see this very particular shape of the spectrum? And what I have plotted in this right-hand picture is the amplitude of this signal. The amplitude of how much energy these photons have gained as they pass through the clusters of galaxies. So each of these, so if you look very carefully, closely on your screen, you will see, so most of this is actually noise. This is not really features, but you see some very bright spots. So there's one bright spot right here where my cursor is now. Right, this is actually a very big cluster. You see some bright spots here. Each of these bright spots is a cluster of galaxies. The CMB, we don't just have information from, we are not just seeing the last scattering surface, but we are also seeing clusters of galaxies which happen to fall between the last scattering surface and us. You see actually there is this big blob here on the top corner. That is actually a Virgo cluster. It is a very big and the most nearby cluster. So again, I will again try to, so this is just, I think, the brief overview of what I am going to talk about. So I will try to explain a little bit more detail, some physics which goes into it, given the time we have. So let us start. So let us start with a little bit of history. So it is interesting to look at history, especially today, because if you have been going to some cosmology talks, you might have heard the words Hubble tension. So there is actually a controversy going on in cosmology right now called Hubble tension, and it relates to the fact that there are different ways of measuring the expansion rate. As we will see, universe is expanding, and how fast the universe is expanding, there is some controversy about the number, exactly how fast the universe is expanding. And this is very closely related to a controversy that happened about 100 years ago, and which actually started this field of cosmology. And the controversy 100 years ago was not about how fast the universe was expanding. Universe expansion was not discovered at that time, but how big the universe actually is. So, so we can say that cosmology started with some facts which were discovered in this early 1900s. And the first fact was that the universe is big. So I don't know how much science fiction you guys read, But if you have heard about this Douglas Adams Hitchhiker's Guide to the Galaxy, I will highly recommend it if you are interested in reading science fiction. And there is a comment here about how big the universe is. So it says, space, it says, is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it is a long way down the road to chemists, but that is just peanuts compared to space. Listen, and it goes on and on and on. And in way, this the author, the Douglas Adams, is right. It is very hard for us to imagine just how big. We talk about numbers. I will talk about parsecs and gigaparsecs. So 1 parsec, so astronomers measure distance is in parsecs. 1 parsec is about 3.26 light years. We talk about gigaparsecs or billions of parsecs, but it's really just numbers. It is very hard for us to intuitively feel how big the universe really is. So it was not easy for people to accept that universe is actually really big. In fact, before 20th century, so before 1900, people had their own small telescopes. So people mostly studied stars in our own galaxy, the Milky Way. And most people believed that our Milky Way, which is the system of stars bound together by their own gravity, this was the whole universe. Right? People did not know anything about other galaxies which may happen outside the Milky Way. So this is a particular picture of Milky Way. If you have, if you go to a very dark place away from any big town, you will see that there is a band of white band, cloudy band which runs through the sky. And that is actually nothing but Milky Way. We see this band because the Milky Way is shaped like a disk, and we are actually inside the disk. So when we see through the disk, we see these too many stars which all just blend together into a cloudy streak that runs through the sky, and that is called Milky Way. And the nearby stars, they appear above and below this band. And you see this dark, there are many dark regions in this band, and those are basically dust clouds. There's a lot of dust in the galaxy, and this dust absorbs this, between us and the stars, it absorbs this starlight. And so there are portions where there are clouds, these dark clouds, they appear dark. But before 20th century, people had actually speculated that there might actually be, mostly by philosophers, that Milky Way may not be the whole universe. There was an astronomer, Thomas Wright. He actually recognized that actually this Milky Way appears like this because it is a disk of stars, and we are actually inside the disk. But there was a philosopher, Kant. So he was very interested in some nebulae that you could see in the night sky. There were some cloudy objects in the sky. So to naked eye or to small telescopes, they just appeared like some clouds which was some spiral structure. And he speculated that maybe there are some island universes, there are systems of stars on their own outside the Milky Way. But there was no way to prove or disprove this hypothesis. By 1900s, people had pretty much measured the size of the Milky Way and come up with almost, so the furthest stars that you could see were about 10 kiloparsecs away. So they estimated that the size of our galaxy was around 10 kiloparsecs. But again, this was not an uncontroversial number. There were many ways to measure the distances to the distant stars, and not all of them were very accurate. So depending on, people did not know which method is more accurate than the other, and depending on which method you choose, you could get a number between 10 kiloparsec and 100 kiloparsec. And there was another thing. So the Slipher, another astronomer, he was looking at this nebulae. Again, the galaxies were called nebulae at that time because people did not know actually that they were galaxies, but they were systems of stars. So he measured the spectra of this spiral nebulae, and by looking at spectral lines, by looking at the Doppler shift, you can find out how much the lines are shifted, whether something is moving towards you or away from you. And he found that they were actually moving too fast to be gravitationally bound. So this speed of this spiral nebulae was more than the escape velocity from our galaxy. Right, so already people were trying to wonder whether these spiral nebulae actually are not bound to our galaxy. And things came to an head. So this was the background for a debate between 1920 between Shapley and Curtis. So Shapley argued that the spiral nebulae are just gas clouds, just like these dark clouds that you see in the Milky Way. Spiral nebulae were also clouds, but they were slightly more luminous because they had more stars in them. But they were still between our universe and within the Milky Way. And Milky Way was actually the whole universe. And Curtis was actually arguing that the spiral nebulae were actually galaxies like the Milky Way, and they were outside. But again, data was not good enough to settle the debate one or the other. And although Curtis was arriving at the wrong, it's very interesting NASA website that you can look at, devoted to this debate, and it is very interesting to see. There's a transcript of that debate and also the analysis by experts, and it is very interesting to see, to read through this if you are interested. So, and if you read through this, you will see that Curtis, although he got the right conclusion that spiral nebulae are the galaxies, his arguments were wrong. Shapley, some of the arguments of Shapley were right, but he was arriving at wrong conclusions. So when data is not good enough, even if you can use correct arguments to arrive at wrong conclusions or wrong arguments to arrive at correct conclusions, and to really settle the debate, you need more data. So really, to settle the debate, really what you wanted to know was, first you wanted to know how big is the Milky Way, then you want to know how far are these nebulae. Right? When you have the answers to both these questions, then you can compare them two and see whether nebulae are inside Milky Way or outside. And to do this, you need an accurate way to measure astronomical distances accurately. And this the current debate that I am talking about a lot about this history, because the current debate that is going on about how fast the universe is expanding is also related to how accurately we can measure the distances. There is again controversy about different methods of measuring distances. We don't know which method is correct and which is not, and we need more data to settle the current debate, just like 100 years ago. So in particular, if you interested, there's a very interesting analysis of this debate, or 1920 debate by Virginia Trimble. It is available on arXiv if you are interested. So how do we measure astronomical distances? Right? You cannot really take a measuring tape and go to the next star. So what we need is some standard candles. That is one way, standard candles or standard rulers. I will come to standard rulers a little bit later. So what are standard candles? Standard candles are objects with no luminosity. So luminosity is energy that, for example, a star, it outputs per unit time. Right, so if a star is emitting some energy per unit time and you observe it at a distance, some distance away, let us say d away, then this energy will be spread over a sphere of distance of area 4 pi r square, right? Which means that the flux per unit area that we will observe at a detector on our Earth will be luminosity divided by 4 pi r square. So if you know luminosity and you measure flux, you can solve this equation for distance. You know the distance to the object. So now the question is to find these objects, standard objects with no luminosity. So the objects with no luminosity are known as standard candles. And so in 1912, Henrietta Leavitt, I forgot to write the full name. So Henrietta Leavitt was an astronomer, and she discovered in 1900s. Unfortunately, she died before her method could be used to settle the debate. But in 1912, she discovered that there are particular kind of stars called Cepheid variable stars. They're called Cepheid stars because first they are found in a Cepheid constellation on the sky, which have a standard luminosity. So these are stars which are going through a particular phase in their evolution. They are very young stars, and they have exhibit radial oscillations. So they are basically oscillating radially. As they oscillate, so their size is changing. Right? So they become slightly smaller, the luminosity decreases, then they expand again. So they are expanding and contracting, undergoing radial oscillations. Now they expand and contract, the luminosity also goes up and down. And it turns out there is a very tight correlation between this period of oscillations and their luminosity. And so if you observe a star and measure its period, you know what its luminosity should be. So this was very good. So it means that if you can find these Cepheid variable stars in these external nebulae, then you can use them as standard candles. You know their luminosity already by measuring, by observations in our own galaxy, by calibrating them in our own galaxy. So if you measure this in a distant galaxy or a distant spiral nebula, when you measure their flux, then you can know the distance to that spiral nebula. So in particular, so this background picture is what is known as small Magellanic Cloud. This is a small galaxy, satellite galaxy of Milky Way. It is bound to the Milky Way by their mutual gravitation. And hence is much, much closer to any other galaxy like Andromeda. So Henrietta actually observed many of these stars in this small Magellanic Cloud, and she observed that, you know, they had all the same luminosity. The Cepheid stars with a particular period had all the same luminosity. So they were standard candles. So Hubble in 1924 was able to use his big telescope I forgot the name of the telescope. I think it was Mount Wilson telescope. And he resolved these individual stars in the Andromeda galaxy and other galaxies also, and proved once and for all this actually they were outside the Milky Way. Even if you assume that Milky Way was 100 kiloparsecs big, these variables are actually much, much farther. They were megaparsecs away. So 10 times more further away than even the biggest estimator you could have of your Milky Way. And then at the same time, Einstein had come up with his theory of general relativity, the relativistic theory of gravitation. And Friedman actually was able to find a solution to the Einstein's equations, which was the expanding solutions. So according to Friedman's solution, the universe should either expand or contract. It cannot be stated. And Einstein was actually not very happy with those solutions. I did not really pay much attention to this. He kept trying to find a static solution to his equations. And later he called this his biggest blunder, because it turns out that there is no static solution to Einstein's equations. The universe must either contract or expand. And Lemaitre, he was able to put everything together. So Hubble's observations and Slipher's observations that, you know, all the galaxies are going away, put together with the Einstein's equations. He said that everything fits together. And in fact, Einstein predicts that the universe should be expanding, and that is exactly what we are observing. And in particular, in 1929, Hubble measured these Cepheid variables in many, many galaxies and produced what is known as the Hubble diagram. So what was Friedman's solution? So Friedman's solutions was what is known as Friedman metric. So metric is just a prescription how to measure distances. Right? In Euclidean, you know that distance between 2 points is x squared plus y squared plus z squared. You can go to spherical polar coordinates, and then in spherical polar coordinates, the distance will be, if you forget about this denominator in these brackets, then the distance will be just dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. It's just dx squared plus dy squared plus d z squared. That is it. Euclidean coordinates, you go to spherical polar coordinates, and the distance becomes this. The metric just tells you how to measure distances. Now Einstein tells us that, okay, space here and time are not separate, they are together, so we should have a common metric for them, and that is known as, so space and time are unified in Einstein's theories, special relativity as well as general relativity. In special relativity, we talk about Minkowski metric, where all the scale factor is absent and this denominator is absent, but if you will get rid of those, you get the Minkowski metric of special relativity, from where you get all the light cones and 45-degree, that light travels at 45 degrees in light cones, right? And the space-like particles, separations, and time-like. And so in general relativity, the metric can have a more general form. In particular, Friedman found that for the whole universe can be described by a metric that looks something like this. So K is the curvature. So universe need not be Euclidean, it could be curved like the surface of a sphere. So we'll not really go too much detail into this curvature, because it turns out that universe is actually flat. So curvature is almost zero. You can forget about that. But also turns out that the universe is dynamic. So the scale factor in front of this is a function of time. This is not a constant. This is a function of time. And the fact that we cannot make the scale factor constant, so we cannot get rid of time in the spatial part of the metric, is just it's just because there are no static solutions to the Einstein's equations. The universe must either expand or contract. So scale factor must be a function of time. So this metric tells us how to measure distances. So if you just look at the spatial part, just like dx square plus dy square plus dz square will tell you how to measure distances in Euclidean space. Here the proper distance will be actually the combination of a and r. Between 2 points, you would take origin and take some distance r away. The point is not, the distance is not r, but it is a times r. So that is the physical distance. So r are just coordinates. These are just labels that you have put given to each point in your space-time, but they don't really have any physical meaning. To get the physical distance, you must multiply, it's given by this full metric element. So it is given by the scale factor times r. So scale factor just tells you how the scale of the overall scale is changing. So usually you normalize scale factor to 1 today, so that all distances that you measure, they are in terms of the distances today. But if you go to past, the scale factor will be smaller, so the distance, things will be closer together, and physical distances will be smaller, even though this for the same r coordinate. Right? So the Hubble parameter we define as the rate of change of the scale factor. This is how fast the universe is expanding. This is divided by dA over dt divided by 1 over a. And then if you take this derivative of proper distance, dr by dt, that is how fast something is moving away from you. So only time dependence is in a, and that at t equal to t0, so Hubble is a function of time, right? As the universe evolves, this expansion rate also changes. But today it has a particular value, which we call h0. Now, if you just take the derivative of this proper distance, you will find that velocity is h times r. That is Hubble's famous relation. It is predicted by general relativity. So Hubble went. So in general, this Hubble will be, a lot of time I'll be using some variable z. Z is just inverse of 1 over a. I will just give a exact definition of that. It is called redshift. I will give a definition in a minute. But this is, so Z redshift is just, again, it is a substitute for time. So at high redshift means earlier times. Like low redshift, so it is inversely proportional to A. So scales, as you go in past, the scale factor decreases, redshift increases, and time also decreases. So it is actually a function of time or redshift, and today its value is 0, h0, which means when we put z equal to 0 in this equation, and we are for a flat universe, omega r plus omega m plus omega lambda. Omega r is how much radiation there is. Omega m means how much matter there is, both baryonic matter and dark matter. Omega lambda is how much dark energy there is. So we put z equal to 0 and put the condition lambda plus m plus r is 1, then you see that today h equal to h0, but in the past it will be different. Okay, so Hubble actually decided to test this relation predicted by Einstein's theory, and he went and he plotted distances versus, actually this bottom line is the distance to the galaxy, and this vertical line is, it should be actually, I think, kilometer per second. The per second is missing, so this is just a picture taken from Hubble's book. And we found that this is actually, again, the data is, you can see, not very good, but he could see that there is a correlation. So there is a correlation, things which are further away are moving faster. And that is what this Hubble law tells you, that things which are, velocity is proportional to distance. So things which are further away, in this coordinate system, we are at the origin, right? as Lemaitre put this together, and he was able to convince Einstein to give up his quest for a static universe, and because the actual universe is actually expanding. And today, so again, a lot of progress has been made. Today we can see much further. We use other standard candles, not just the Cepheid stars. Although they are very bright, we cannot really see them very far away. So we use supernovae. Supernovae are exploding stars, and they're as bright as the whole galaxy. So we can see them actually much, much further away than Cepheids. And here it is plotting as distance. So again, so vertical line is the y-axis is basically, again, a measure of distance in some funny units. So d is the distance. There's like a logarithm of distance. Astronomers use magnitude to measure the brightness of this star. And the further the star is, dimmer it will be. So how dim the star is related to its distance. And that is what is shown here. So M is like so in the standard candle formula, I showed you luminosity and flux. This capital M is like luminosity, little m is the flux that you measure. And if you know both, if you know M, the luminosity or capital M, and flux, this little m, you can solve this equation for distance. Instead of solving for distance, astronomers just plot this m minus m. And the redshift is defined as just by related to scale factor as 1 plus z. So today the scale factor, we normalize scale factor equal to 1, which means redshift today is 0. Redshift just means that the photons which are coming to us from further away, their wavelength gets shifted towards longer wavelength by a factor 1 plus z. So if we had emitted visible light, it means the visible spectrum of a star will be shifted, will become redder for things which are further away. So that is why it is known as redshift. Or if something was moving towards us, then the visible spectrum will shift towards the blue end of the spectrum. So we will call it a blue shift. But because we are in an expanding universe, things are further away, they are redshifted. So that is called redshift, and this is what relates. So in 1998, actually, Rees et al. And Saar Perlmutter et al. This plot is from this Rees et al., but there are two independent groups. They found something surprising. They found that as with time, the universe, the expansion rate is actually increasing. If you take the second derivative, or the derivative of the Hubble rate, or the second derivative of the scale factor, that is acceleration, it is greater than 0. And that is very surprising because you see that gravity is the attractive force, right? If you throw a ball from Earth, its velocity will decrease as it goes further and further away. That is, it is going away. If its velocity was less than escape velocity, it will reach a maximum height and then fall back. For things which are moving apart, gravity tries to pull them together, which means things which are moving apart, they should slow down until they maybe come to a rest. If it was a bigger, the velocity of the ball was bigger than escape velocity, it will escape to infinity. But as it is escaping, its velocity will still keep on decreasing because acceleration is always pointing away from the direction of velocity. And this is true for any things which are, all things which are moving apart. In expanding universe, basically things are moving apart. Gravity should try to slow things down. And what people found was that very early on, in the very early universe, things are indeed slowing down, but at some point they change direction. And things started speeding up again. That is very strange. And this was this was a very strange discovery, and actually they got Nobel Prize for this discovery. So what this discovery means is that there is something that does not behave like normal matter. So the gravity of normal matter or radiation, Einstein's theory tells us that gravity is always attracted for normal matter or radiation. But you can have some exotic field in the universe. One example is a cosmological constant or vacuum energy in the quantum field theories. And these have actually negative pressure. The pressure is negative of the energy density. Normally pressure is always positive. This negative pressure means, so Einstein's theory actually neutrons gravity, only mass or energy has gravity. But in Einstein's theory, pressure also gravitates. Pressure is also important. If pressure is negative, it means that it can actually make the universe accelerate. So this acceleration, so we don't really know what dark energy is. So this is just a game name that we give to this accelerated expansion of the universe. But it could be anything. We don't know actually. So future experiments will tell us what exactly it is. It could be just a cosmological constant, which means that in Einstein's equations, it's just one constant of unknown origin. Just like another fundamental constant of nature, just like electron mass or electron charge is a fundamental constant of nature, or the interaction strengths are fundamental of standard model of particle physics, are constants of nature. Standard model of particle physics does not really predict what those interaction strengths or masses of particles should be, particular mass of electron. So cosmological constant also can be just like Newton's gravitational constant. It can be another constant of nature that appears in Einstein's theory of gravity. But that is not a very satisfactory solution. And people are trying very hard to actually find deviation from this, to find an anomaly. That is why this cosmological constant is called lambda. So that is why the standard model of cosmology is called lambda CDM model. So lambda comes from this dark energy, and the CDM is the cold dark matter. So there is two new constituents of the universe that actually cosmologists have already discovered. You can say two new particles. One is dark energy, one is dark matter. Right? They don't exist in standard model of particle physics. But it could be something dynamic. So it could be some dynamic field. Something, some scalar field like a Higgs field, for example. Or it could be some modification of gravity. Maybe Einstein's gravity is not the right theory, and that is why we are seeing this unusual result. If you just modify the Einstein's theory of gravity, everything will fall in place. So it's just that we are getting this cosmological constant because we are using the wrong theory of gravity. It could be modification of gravity, some new particle, or just cosmological constant. We don't know yet. Okay, I think we are already more than half of my time.
Yeah, it's exactly half. I mean, 5 minutes more, nothing.
5 minutes more than half. Okay.
Yeah.
So hopefully I will be able to get to at least this current debate. We talked about this 100 years ago debate. Hopefully I will, so there will be a few minutes to say something about the new debate also. But let us look at this expanding universe a little bit more carefully. If we extrapolate backward, then the universe should become denser and hotter, right? It is just, the universe is the whole system. So as you go backwards, you should just, things will become hotter adiabatically, just like, get glass in a box. If you expand the box, things become colder. If you compress the box, things will become hotter. And in 1948, Alfred Gamow and Hermann, they actually, so they were trying to solve the mystery, how to produce these new elements. In particular, how to produce helium in the universe, all the helium that we see. So people did not really know at that time that, some people thought that, you will produce most of the elements in the stars, inside the stars. But Alfred Gamow and Hermann thought that maybe actually you could also, as you go to early universe, it becomes denser and hotter, just like the center of a star. And you can also cook protons and neutrons into helium. And they calculated what is the temperature will be needed. So free neutron is not a stable particle. Right? It has a lifetime of around 900 seconds. So which means that all this cooking will have to happen at the fusion of hydrogen and neutrons will have to happen at time less than 900 seconds. And the temperature that you will need will be about billion Kelvin. So then so if you then to look at take the age of the universe or the expansion that was the model that was arrived at by Hubble, and you say, okay, at 900 seconds, temperature was 10 to the 9 Kelvin. So what will be the temperature of this? So there should be radiation also that should be there in the universe. What should be the temperature of this radiation today? And they calculated that this radiation should have cooled down to actually few kelvins today. So this I would call the first great theoretical prediction in cosmology. first non-trivial cosmological prediction in cosmology. They predicted that cosmic microwave background should exist. So black body spectrum with few Kelvin temperature, it will actually peak in microwave frequencies. So they predicted that there should be cosmic microwave background that should fill the whole universe. Right? So we are extrapolating universe backwards, and at some point you will reach t equal to 0, or when scale factor goes to 0. It turns out that you reach scale factor of 0 or infinite density in a finite amount of time. And that is when you start your clock, so t equal to 0, and it is a hypothetical origin. Hypothetical because before that happens, before you reach infinite density, actually we don't know what will happen there because we don't have a theory. We have only tested our particle physics models up to few TeV temperatures. When temperatures become bigger than TeV, bigger than what we see in the Large Hadron Collider, we don't know actually what will happen, what the particle physics will look like. In particular, as you might have heard in the previous talk, that when you go to Planck scale, you would expect that some quantum gravity effects will start becoming important, and we do not really have a good theory to calculate things like that. So this is still hypothetical. So this is the, so that is why this is a question mark. This is a picture from particle data group. So this is a hypothetical Big Bang, but a little bit after Big Bang, even just a few seconds after Big Bang, we can actually start applying our particle standard model of particle physics. So we know that very early universe, you should have some quark and gluon plasma. Right? The quarks and temperature will be high enough that this quark and gluons will be free. They will be deconfined. But at some point that cools down, then these protons and neutrons will condense out of these quarks and gluons. So these are shown in these quarks here. As the temperature cools further, these protons and neutrons will cook into, so all the neutrons will actually go into helium atoms, and the remaining protons, they will be just the hydrogen ions. So we will have helium ions, hydrogen ions, and free electrons, as well as neutrinos and antineutrinos. So early universe, you also have tau particles and muons, but all of those are, and W and Z and all the standard matter particles. By the time, so this is when the cooking of protons and neutrons into helium and some other elements, like you produce a little bit of deuterium, little bit of lithium also. That is known as Big Bang nucleosynthesis. So Big Bang, and there's a nucleosynthesis means you are cooking the nuclei. In fact, lithium is a very fragile element. So all the lithium that you have in your batteries, in your cell phones, in your laptops, in your computers, all the lithium is actually coming from this about 3 minutes after the Big Bang. All that lithium was cooked, it was made about 3 minutes after the Big Bang. Stars cannot make lithium. Lithium, in fact, they destroy any lithium because stars are too hot and dense. That actually, any lithium that gets into a star, it gets destroyed. So they are not destructors of lithium. So all the lithium that we have, so you have actually a piece of, all of you have a piece of Big Bang in your pockets. Evidence that universe was particles which were created when universe was just few minutes old. You see the time scale here, this is 100 seconds here. So between, yeah. So as the universe cools further, then these electrons, so the binding energy of nuclei is of all the mega electron volts. So that is the temperature here when you are cooking the first elements. Then the hydrogen atom has the electron and proton have a binding energy of 13.6 electron volts. So when the temperature becomes of order electron volts, then the electrons and, so before that, electrons and protons cannot really combine together. Because as they form a hydrogen atom, a photon will come and ionize with more than 13.6 electron volt energy, and it will ionize the electron. So this, the background photons, the CMB photons, which have at that time more than 13.6 electron volt energy, they don't allow the electrons and protons to combine together. But once temperature cools below electron volt, these photons disappear, and the electrons and protons, if they combine, then they can live in peace. There's no photons around to separate them apart again. So before this is known as recombination, the combining of electrons and protons into hydrogen atom. and electrons and helium nuclei into helium atoms. This is known as the recombination. And this is where the CMB photons are coming from. This is what is known as the last scattering surface. It happens when redshift is around 1000 or when universe was around 380,000 years old. So before this last scattering surface, the electrons are actually all free, right? And the photons have actually very strong interaction with the electrons. So for this Thomson scattering cross-section is very high. So as long as you have free electrons, the photons will scatter off each from them. So it is like photons are living inside a wall where they cannot really go much further. They go a little bit further, so they are scattering in a sea of electrons. So they scatter from electron to electron and can't really move very far. But once the electrons combine into hydrogen atoms, suddenly these free electrons disappear, and the hydrogen gas is actually, the neutral hydrogen atoms are actually transparent to the CMB photons, to the photons below 10 electron volt energy. So as soon as the universe recombines, these photons are free to travel to us. That is what is shown here in these photons. So earlier these photons are going in random direction, but once universe recombines, they come straight to us almost. So that's why this is the last scattering surface, and the photons are coming straight to us from this surface. For that, they were undergoing random scattering, but from here they are going straight to us. So that is the picture they are bringing to us. They are bringing to us the picture of this last scattering surface, where the universe was around 380,000 years old. So what does the CMB look like? So if you look at the sky, so the first experiment was this Cosmic Background Explorer, or COBE, which flew in 1990. 1989, 1990, it took the data. So it looked at the CMB sky. It found that, let me see, it found that actually the sky looks uniform all over. So the CMB has same temperature in any direction that you look. And temperature was around 2.7 to around 3 Kelvin, 2.7 Kelvin. Right? So this was this was very strange because and I have time to go into details, but it's not easy to see why the universe should be so so smooth or so uniform. Because if you look at one direction and then you look at completely opposite direction, and the photons from there are coming to us just now. And the photons coming from one direction, which are coming to us now, would have no way of knowing what should be the temperature of the photons at the other end of the universe. Right? They were not causally connected. The photons are just reaching to us now. So there was no way for the distant parts of the universe to know what temperature they should be in. So it is not clear why the universe looks same in the opposite directions. It turns out that we can solve this conundrum why the universe looks so simple or so uniform if you have something like accelerated expansion in the universe, just like the dark energy, which is the accelerated expansion today. If very early times, there was actually exponentially accelerated expansion, then it turns out that that would explain how why the universe is so big, because it turns out that what accelerated expansion does, it takes a very small patch and blows up into a whole universe. So all of the fission tells us that all of our universe came from a very, very small patch, and that is why before inflation, that patch was in causal contact. Then the different parts of that patch could talk to each other. It is only today that it seems to us that they are actually out of causal contact, but it is not really so. So inflation restores causality. I will not say too much about inflation. But actually, so if you subtract out this 2 to 3 Kelvin background, we start to see some anisotropy. We see that CMB is actually, over and above this 2.7 Kelvin, CMB is slightly hotter in one direction by about 3 millikelvin, slightly colder in the other direction. That is just because we are moving with respect to the CMB. So just the Doppler shift of the CMB photons in one direction. So it tells us that we are moving with around 300 kilometers per second with respect to the CMB. If you take away this dipole also, which is trivial, is just the Doppler boost, because we are not at rest with respect to CMB, but moving. we start to see this micro-Kelvin anisotropies. And if you have gone to a cosmology talk before, you would have seen this this picture before. This is the map of the sky that is made by a Planck experiment, which is the latest CMB experiment. But you see all this, as I told you in the beginning, these are all 100 microkelvin fluctuations on the sky on top of this 3 millikelvin dipole and 3 Kelvin average background. And there's a lot of information in there. I will come back to that. And this was the picture at 380,000 years ago. It turns out that these are the fluctuations in photons, but matter, or the baryons, the hydrogen and helium gas, as well as dark matter, they will also have similar fluctuations. So some parts of the universe will be denser than the other. And then the dense parts, as I told you, gravity is attractive. So wherever you have high density, that will try to become more denser and denser until it collapses and forms galaxies and stars. And that is what happens. So CMB is around 380,000 years ago. And at some point, so nothing much happens. This over densities or this high density peaks in the early universe, they just collapse and become denser and denser. And at some point of time, there are regions in the universe which are dense enough that they form galaxies, and then the clouds, the gas inside those galaxies collapses and starts forming stars. And that is where we form first stars around 400 million years after the Big Bang. So Big Bang is our t equal to 0. So when the stars form, they actually, so remember, so the universe had become neutral and transparent to CMB. It turns out when the stars form, they again start pumping ultraviolet radiation into the universe, photons which have energy more than enough UV, 13.6 electron volts and greater, which can ionize the hydrogen. So you start reionizing the universe, you start recreating the electrons, free electrons, and so small number of actually about 6% of the CMB photons, they scatter again from this newly formed, newly freed electrons before they come to us. And we see actually the effect of this scattering. So this is like a blurring screen. Right? So this is like if you are looking out of your window, right? If you have a clear glass window, then there's no scattering going on inside that glass. You see a clear picture outside. But if you have a slightly translucent window that you usually have, for example, in your bathroom windows, they are usually translucent. What is happening there is it's inside the glass. There's a molecular structure is such that the photons which are coming from outside, they are getting scattered again. And it blurs the picture that you see outside. This is exactly what happens here. So the reionization, so this is known as the reionization when the first stars ionize the universe again. It blurs our picture of the CMB slightly. And it blurs it in a very particular way. And by just noticing how the universe is, this CMB is getting blurred, we can actually, we know exactly when the stars were, first stars formed. And it was exactly 400 million years. There's a lot of information in the CMB. And again, so you're forming galaxies until we go today. This WMAP was the second CMB experiment. So first was COBE, then came the WMAP, the inner space, and the third was the Planck. So this is a publicity picture by NASA and WMAP science team made by, and right now, so you see that the universe is getting slightly accelerated, so it's expanding faster right now, and they have sketched that also here. Okay, so let us recap a little bit before going further. So COBE was the first precision CMB experiment, you could say, and told us that there are anisotropies in the CMB, the 100 microkelvin anisotropy. It measured the spectrum of the CMB and found out that actually it was a almost perfect black body. It could not measure any deviations from the black body. Before that, CMB was discovered in '65 by Penzias and Wilson. That was also a Nobel Prize. So between '60s and '90s and COBE, there are numerous efforts to measure the CMB spectrum as well as anisotropies, these fluctuations in temperature. The real success, the precision measurements came with COBE from space. There was also actually a Canadian rocket experiment. They did not go to space, but they just put a CMB experiment on a rocket, and this rocket went out of the atmosphere, took data, and then and it fell back again on the Earth, and it actually was almost as good as Kobe. But their results were slightly delayed. Kobe was first, so they got the Nobel Prize, and Cobra. So I think they were just a few months before Kobe. Maybe they would have shared their Nobel Prize. In particular, they found that they also found that CMB spectrum was almost a perfect black body. So after that, there was a tremendous progress. So there were WMAP, Planck, SPT is South Pole Telescope. It is on the South Pole, CMB experiment. ACT is Atacama Cosmology Telescope. In the Chilean desert, in Chile, is the Atacama Desert, and there is again a telescope there. Then Boomerang was a balloon. So similarly, you can put a CMB experiment on a balloon, and it goes out of the atmosphere and then makes precision measurements. And then again, lots of so CMB is also polarized. It is not just temperature fluctuations. I will not go into this, but those have also been done. And all this effort has led to the standard model of cosmology. And now the next big task is to find out anomalies. So B modes is something, the gravitational waves, you have heard about. LIGO detected some gravitational waves. These are classical gravitational waves. But the inflation predicts that there should be some quantum gravitational waves, or the gravitons in the early universe. Just like during this accelerated period of expansion, you should produce quantum excitations of the gravity, and you should produce these gravitons. And this structure, gravitons leave a unique signature in the CMB, in the polarization of the CMB, these photons, which are known as B modes. There's a particular pattern of polarization, which is the B modes. This also again, so this is a slide summarizing the standard model of cosmology. So standard model of cosmology, we can say it consists of following ingredients: the standard model of particle physics. We add it to it general relativity, and you add to it cosmological principle. Cosmological principle means that we are not in any particular special place in the universe. The universe should look same to an observer in Andromeda as it looks to us. In particular, we are not in any center of the universe. Every point is as good a center of the universe as us. Plus, that the universe is flat. This is also, so cosmological principle is also verified, roughly verified observationally. Flatness, again, by looking at the CMB power spectrum, we know that universe should be flat. There should not be any curvature. You add to that some inflation, which is some accelerated universe in the accelerated phase of the universe in the very early universe, which is defined by some two new parameters, two free parameters you have to add. You have to add cold dark matter. How much this cold dark matter means? Cold means that the particle velocities are very, very non-relativistic. Dark means that it does not have any electromagnetic interactions or strong interactions. It could have weak interactions. And it is a matter. Matter again just means that these are massive particles. They cannot be massless particles like photons. They have to be massive particles. We add to that a cosmological constant or some other parameter for a dynamic dark energy. And to that you have to add something called baryogenesis. Baryogenesis refers to the fact that for every one proton or neutron that we have in the universe, we have 10 to the 9 CMB photons. Why is this ratio so large? Why is there this small asymmetry? Or you could ask actually, why is this ratio is what it is? So any early universe theory of inflation or particle physics that you can cook up, usually it is very difficult. Normally you would expect that, if you started with equal amount of matter and antimatter, all that matter and antimatter will annihilate each other. You should not have any matter left. So why do we have this little bit of matter left? Even though it is small, it is still quite large. In fact, if you test a standard model of particle physics, it will predict actually much, much bigger ratio of photons to baryons than this. So this is again an unknown physics that we must put into. We don't know what exact mechanism it is. It is not in the standard model. This is baryogenesis. So all these features are actually beyond the standard model of particle physics. You can see that cosmology is already very successful in discovering new physics or hints of new physics. It requires new ingredients beyond the standard model of particle physics. So standard model of particle physics cannot be complete. There should be actually there should be a lot beyond this. So there's a lot of things to explore. To this, we have to add some new parameters. I talked to you about reionization. So the optical depth to reionization, which just means that what fraction of CMB photons, how much blurring there should be. That is a free parameter we have to add. And we can actually measure this with CMB. And the Hubble constant, which is the current expansion rate of the universe. So if you count 2, 3, 4, 5, 6, the 6 free parameters and some extra ingredients that usually we sweep under the rug makes up the standard model particle. But there are no free parameters in there. These are just observations. So the baryogenesis, 10 to the 9 photons per baryon, just the observation. We can't really do anything about this. So there are only 6 free parameters that we adjust. And as we adjust the parameter, as you saw in the first slide, the CMB power spectrum changes. And by fitting this power spectrum, the observed power spectrum to theory, we can fix the value of these parameters. And that gives us the standard of cosmological physics. And as the precision improves in the future, we hope to discover some deviations from this standard model, and that will be discovery of new physics. So how much time do I have? I think I'm almost out of time.
Yeah, you are just out of time, but it's all right. We don't have that hard and fast
Okay.
time.
I will just take 5 minutes, 5 more minutes.
Yeah, sure, because you are almost there. So please continue.
Yeah. Yeah, so actually I have a lot of slides, but I think many of these slides are very technical. And I don't really want to go into technical details. I just wanted to give you a flavor of what is happening. So earlier I had showed you some sketch of the universe, which was a theoretical, what a theorist would make. Now I am showing you a sketch which an observer or experimentalist would make. So from an experimentalist or an observer's point of view, we are at the center of the universe. It does not mean that we are in a special place. If you have an observer in Andromeda or some faraway galaxy, it will also make a same picture. The universe will look exactly like the same to every observer in the universe. So universe is isotropic. I have plotted redshift here on one axis, time on one axis, and the temperature on the third axis. So as we are go away from center, we are looking at further and further away. So we are able to look at bigger and bigger volume of the universe, right? It's not just the universe is contracting as you go, right? Redshift is increasing, but what I am presenting here is the observer's perspective. So as we go, as we look further and further away, we are looking at further and further away in time. So this is the time after the Big Bang, or when the universe was smaller and smaller, so higher and higher redshift, and we are looking at a bigger and bigger volume, right? So at 24 seconds, actually all electrons and positrons, so the mass of the universe, the temperature drops below 500 kilo electron volts, which is the mass of electrons. So before that, photons can produce electron-positron pairs. But after that, all electrons and positrons annihilate, except a small number, 1 in 10 to the 9 electrons survive. So that is the baryogenesis. That is the matter-antimatter asymmetry. So for every 10 to the 9 positrons, there were actually 10 to the 9 plus 1 electrons in the universe. So 10 to the 9 electrons annihilated with 10 to the 9 positrons, and the 1 electron remained. So these remaining electrons, they will then recombine with the protons and helium nuclei to form neutral atoms, and no positrons remain. Right. So it turns out that at very early universe, the universe is also very much in equilibrium, which means CMB. So perfect equilibrium means the CMB will be a black body spectrum. At around redshift of 2 times 10 to the 6, which is at around 70 days after the Big Bang, it turns out the universe has become cold enough, and it is not dense enough to maintain that equilibrium. So if CMB, so what that means is that if you now disturb the equilibrium of CMB, we put in some disturbance in the universe, For example, some black hole which explodes or evaporates by, or there is some unstable particle which decays and introduces high energy photons into the universe, it will create a disturbance in the CMB spectrum. This energy will actually heat up the electrons, and electrons will interact with the CMB, and they will distort the CMB spectrum that I told you about earlier. And this disturbance, if it happens before 70 days, it decays away exponentially. But if it happens after 70 days, then it cannot decay away, it persists. And by looking at the CMB spectrum, we can actually see it has information beyond the last scattering surface. So the black body part of the spectrum, CMB spectrum, is giving us information from last scattering surface. If you look at the spectrum was modified much before that. And we can actually look beyond the last scattering surface. And this is quite amazing. And we can actually go not just up to redshift of 1,000, but redshift of million. Or not 380,000 years, but we can look at even further in the past. The universe was only 70 days ago. And Big Bang nucleosynthesis, I told you about lithium. And it actually allows you to look at, it has information about what the universe was like. It was 4 minutes old. So I told you about standard candles. It turns out that CMB is actually like a standard ruler. There's a particular scale, the horizon size, or how far the sound waves. So in this plasma, before recombination, electrons and photons are colliding with each other. The whole plasma is oscillating. There are sound waves in this plasma, and there's particular sound speed, and how far the sound can travel in the lifetime of the universe, in this early universe, that is known as sound horizon. So the sound horizon actually provides a particular scale that I am calling R star. So we can calculate this sound horizon. This is a fixed scale in the early universe. And then if you look at what angular scale, so we cannot really measure this R star today. The R star comes from the theory of sound waves in the early universe. We understand the physics very well. We can calculate this R star. And we measure what is the angular scale at which we are measuring this. So we measure theta. We know R star, which means we can find out how far the last scattering surface is from us. We can find this distance. So CMB is like a standard ruler. And if you know two things, we can measure the distances. So we can actually use CMB to measure distances, in particular distance to the last scattering surface. And this distance actually has measured, so I will not go into this. So the spherical, I told you about spherical harmonic transform. So this L mode, so L is like the Fourier counterpart of theta, is like 1 over theta. The Fourier mode, the L mode at which we see this particular scale. And to be more rigorous, it comes from the spherical harmonic transform of, if you have an x variable in linear x variable, you take a Fourier transform, you get k. For theta phi, you do a spherical harmonic transform, and you get L and M. L same L and Lm, the orbital quantum number that you see in your quantum mechanics class. So you can make this power spectrum, and we see these very particular features, and in particular this first peak, it is actually related to this R star, the sound horizon. And let me go further. So I told you, okay, I will just not go into technical details, but these fluctuations, these oscillations in the plasma, and you can imagine they are defined by an equation which looks like the spherical harmonic oscillator equation. So if you forget about this, you look at only the light blue parts, forget about this forcing term, and this is some damping term or friction in the oscillator. It's just the oscillator equation, and these solutions are cosines and sines. It turns out that the initial conditions are such that only cosine term remains. Right? So general solution will have both cosine and sine, and the boundary condition or initial condition will tell you what is the amplitude of these cosines and sines. And turns out the amplitude of sine is 0, and amplitude of cosine is finite. And this, so this cosine has some k value. Cs is the sound speed. Eta is the time. So Cs times eta is the how far is R star. It is how far the sound can travel. So these peaks that we see, they are actually the extrema of this cosine. Whenever a cosine has a maximum or minimum, you see a peak or dip here. Okay, but you see that this is not everything. So there is a forcing term in this. The gravity, any matter particles that will have, or neutrinos, or anything that is there, it will have its gravity. That gravity will affect this oscillator. So gravity acts like a forcing term. So it is a forced oscillator. And then you have friction term. So the expansion of the universe also affects how these oscillations behave. So there are many ways to, so it knows about how much matter there is from this forcing term, how many baryons there are from the sound speed, as well as the gravity of this, how much radiation there is, the radiation, the ratio of baryons to radiation tells you what the sound speed will be. So theta is temperature fluctuations. Is the fluctuations in energy density. So theta is the delta T over T. So fluctuations about the mean, fractional fluctuations about the mean in the CMB sky. Then each K mode, as I've told you, so R star is related to this K mode, right? And this will, R star will go to theta, so and K mode will go to L. So the K mode corresponding to a particular R star, the extrema of this will correspond to a particular L mode, and that is what we see in this CMB spectrum. In the presence of dark matter, it turns out it changes the zero. So what we observe is some oscillating part plus so if you have only oscillations, so what we see is the power spectrum. Power spectrum is just square of this oscillation. If you square this, we have cosine square. You see that all these extrema will have the same amplitude. But what dark matter does is it introduces a slight change in the zero. It shifts the zero. Because at some points it forces things to compress further than they should. So at one extrema, it makes the oscillations go further. But at other extrema, it makes the gravity of this dark matter makes the extrema smaller. When you square this, this first peak will become larger. The second peak, we're just shifting the zero. Zero from symmetrical. So this oscillation instead of symmetrical will be around the zero. They become asymmetrical. Right? This is just a constant piece added to the cosine. That introduces the asymmetry, and this is the asymmetry that we will see actually in this power spectrum. So your first peak is higher, second peak is lower, third peak is also slightly higher. So this odd-even asymmetry. And that tells us actually that there is actually dark matter. It tells us that the amplitude of this and these relative amplitudes of these different peaks tells us that there is dark matter. Dark matter has to exist. You cannot have modified gravity. Modified gravity, if you have heard, someone has heard about MOND, that is ruled out. There has to be new particles. There have to be dark matter. It tells us just exactly how much dark matter and how much baryons there should be. So in particular, so this distance to the last scattering surface, we have to calculate in an expanding universe. So it is the integral over the Hubble. The sound horizon is also a particular integral over this Hubble parameter that I showed you. In particular, it knows about the Hubble constant. You can measure all these parameters simultaneously, and you can measure the Hubble constant. And it turns out the Hubble constant that we measure from CMB is slightly smaller than what we measure directly, but using the similar method similar to Hubble. But just looking at how far the galaxies are going away from us, and this is known as Hubble tension. And the main thing is that actually we are not sure about the distances to the galaxies. So the Hubble law, you have to measure velocity as well as distance. Measuring velocity is easy by using just the Doppler shift of spectral lines. Measuring distances are hard. That is the problem here. And hopefully there will be new things. There's a 4 sigma, 4 standard deviations away from each other. It is a significant anomaly. And maybe this is that one of the measurements is wrong, or maybe there is some new physics. And many types of new physics people have talked about. I will not go. So you could have some funny form of dark energy which dominated the universe earlier or at late times. So you have early dark energy or late time dark energy. Something very funny going on with the dark energy, or some new particles, relativistic particles in the early universe. Not dark matter. Dark matter is a non-relativistic particle. Or you could have some, what we propose, that you could have some new let's say new interactions in the neutrinos. If neutrinos interact with dark matter, it turns out that can also shift the value of these peaks. If you shift the peak, you change the value of Hubble. The Hubble constant is telling you basically the position of peaks is telling you what is the value of Hubble constant. If somewhere to change the position of the peaks, I will not go into the detail, but you can actually solve this Hubble tension. Okay. And similarly, so this is like an example of an anomaly in the CMB anisotropic CMB power spectrum. Similarly, we can look at anomaly in the CMB spectrum, maybe distortion from a black body. So Kobe measured black body spectrum very, very precisely. It found no deviations at level of 1 part in 10 to the 4. But if you look at parts, as we showed you in the first picture, if you look at clusters of galaxies, we see there are electrons there. We scatter the CMB and they move low energy photons to high energy. So there's a dip. If you change the difference between these two spectra, there will be a dip at low energies and a peak at high energies. So that is the spectrum. But at early universe, we could have some exotic processes like particle decaying or primordial black holes decaying that could also heat up the CMB and create spectral distortions. We should calculate actually the just like the cosmic ray showers in our atmosphere. These high energy particles will generate showers in the early universe, and this will give to very peculiar spectral distortion shapes. By looking at these distortions of the CMB from a black body, we can find out whether something exotic went on in the early universe or what the nature of this process was. Particularly, we can find out if there were any new particles, unstable particles, which were decaying in the early universe. We can look at, let us see, if we have primordial black holes, so they evaporate by Hawking radiation, and they can produce all these standard model particles, which can again heat up the CMB. And so we can put limits on how many primordial black holes there are of different masses in the early universe by looking at just CMB. So these are different limits that we have shown. So basically, how much dark matter can be made by these black holes, and we see that limits are very, the low mass black holes can form only a very small fraction of the dark matter. They cannot have a very high energy density relative to dark matter. So again, so we can also inject high energy neutrinos in the early universe, and there is way again to so neutrinos actually have slightly different signatures. I will not go into this. I will just, I think, end here. Sorry for taking a little bit more time. So again, so in the last 100 years, we have made a lot of progress. Just to so just like the standard model of particle physics, we are now a standard model of cosmology. And just like in particle physics, people are looking for anomalies, some deviations from standard model that will tell you some new physics, what happens at higher energies. Similarly, in CMB also, we can look at anomalies, deviations from the predictions of the standard lambda CDM cosmological model, and that will tell us something about new fundamental physics. We are already seeing one anomaly, which is the Hubble constant, which is the most significant anomaly that we are seeing, and it is real. It is very exciting, especially for theorists, because you can now get creative and try to see what kind of new physics can solve this Hubble constant. But again, we are not sure yet. The situation is very similar to 100 years ago when Curtis and Shapley were not sure who was right and who was wrong. Some, maybe we are arriving at right conclusions, but using wrong arguments. Arguments are wrong, but conclusions are correct. Again, but we need more data. Just like in 1920, you needed more data, and Hubble came up with new data. So similarly, there is a group of Wendy Friedman, who actually recently gave a talk here at TIFR. They are finding a new way of measuring new kinds of stars called the red giant stars. They have shown that actually they can also be used as standard candles. So these are new type of stars, which may have different sources of errors than the normal CFIT-based measurements. And there are also direct ways of measuring using gravitational lensing also to measure the Hubble constant. And maybe next few years, it will become clear whether this Hubble tension is real or not. And I will stop here. Thanks.
Thank you, Dr. Khatri, and I sincerely hope that CMB anomalies measurement will really point towards some new physics we are looking for in the beyond standard model. And now it's the time for taking a few questions. And yeah, so one of the students, Satyam Agrahari, he was asking, sorry, where, yeah. So he was asking a question about dark energy and dark matter actually. And Shatyam, if you are there, you can unmute and ask your question because it looks a bit confusing to me. So you can put your question directly to the speaker. And anyone else, you can unmute and speak. I mean, we can take 2-3 questions
Yes,
before.
ma'am.
Yeah, sure.
For the
I think it will be good if people raise their hands and then ask one by one.
yeah, sure.
Without confusion. Yes.
Hello, sir. Hello.
Yes, please go ahead.
Mm, uh, Sir, from thermodynamics, we know that 100% conversion of energy is possible only in case of conversion of mechanical energy to heat energy. But last time I have attended a webinar where the professor has said that there may be interaction between dark energy and dark matter. If there will be an interaction like by using Einstein's mass energy equivalence, and then there should be a possibility of release of energy. What will be the form of that energy?
Yeah, so we don't know actually. So it will depend on what dark energy is, right? So suppose dark energy is some particle, let us say some new scalar particle, just like dark matter is some new massive particle. Maybe dark matter is a fermion, dark energy is a scalar. Then you are right that in principle it is possible that there is some interaction between dark matter and dark energy. And then what that interaction will do will depend on the nature of the interaction, right? So anything is possible right now. So you can put some limits.
Yes,
we know that, okay, all of dark energy cannot decay into dark matter, or all of dark matter cannot decay into dark energy, because then all our observations will contradict that. But some interaction is certainly possible. So we have upper limits. So people do think about this. And there are upper limits on what kind of interactions are possible. But any interactions that are there, they have to be very small. Right, so far we have no evidence for dark matter, especially for dark matter, that it interacts with anything. So for dark matter to interact with anything, including dark energy, the limits are quite strong.
Then we can calculate the various parameters. If there is a release of energy from the conversion of dark matter to dark energy, we can calculate the various parameters by using the perturbation theory.
Yes, we can do that, and people do that. So there is decaying dark energy models or decaying dark matter models, and people try to. So actually, I think there are some models of Hubble, this is solving Hubble tension, which rely on, I forget, some dark energy decaying or dark matter decaying, or neutrinos have some interaction with dark energy. So in particle physics, if you have two particles, at some level, they will interact. The question is only how strong those interactions are and whether they leave an observable effect. So far, we don't have any evidence of that.
Sir, as I am new in astrophysics, I have one more question. And that astronomical units are measured in astronomical AU, parsec, and light year.
Yes.
So, sir, is it like this that parsec is measured for very excess large distance, and light year is measured less than the distance between for parsec and?
That is just a matter of convention, right? You have, so you have centimeters, inches, foot, kilometers. So there's no, you can measure anything in any units, right? There's some constant conversion factor between different units. It's just that there's convention. So due to different conventions, usually distances between planets and sun, it is easier to measure in astronomical unit because that is how it is defined. It's average distance between sun and earth. If you are looking at distances between stars, then it's easy to think about how much time light takes to travel between the stars. And actually the distances are of light years. So it is then easy to think about in light years. And if you go further, then people talk about parsecs and gigaparsecs and megaparsecs. There's no reason you cannot talk about it. You can talk about distances between galaxies, either in parsecs or light years, or you can even talk about centimeters. Actually, if you go look at astronomers don't like to use, the professional astronomers, especially theories, they don't like to use parsecs. They actually measure everything in centimeters.
Yes, sir. Thank you, sir.
Yeah.
This is more of a matter of convenience. The distance in whichever unit you express. I mean, once you use it, you use share with the community the common thing people are using. Use that. This is a matter of convention, more or less. So yeah.
You can say that your height is 6 feet or 170 inches. Doesn't really matter. It's just what you are used to and what is convention in that particular field. In astronomy also, there are different subfields where people use slightly different conventions.
I can see right now we had some we have some international participants, and I could see one actually. Mr. Shumir, you have any question from Dhaka University? One participant is there right now.
Hello, Professor Khatri.
Yeah, have any question? We were asking for slides. But,
Hello, Professor.
Yes.
In the baryogenesis process, you talk about some asymmetry. I have read this, but now do we have any reason why did asymmetry take place? I mean, why did baryogenesis happen in the first place?
That we don't know, right? We know it happens because we exist. We see only matter. We don't see any antimatter in the universe. If there was any antimatter, then where matter and antimatter meet, they will annihilate, right? And they will leave signatures in the CMB sky. They have matter domains and antimatter domains, so we don't know. So we see that the universe has only matter, and it is observation. Now you need some theory to produce this. We have to produce this. There's no way around it. And the question to why it happens, it has to come from some theory beyond the standard model.
We are looking for physics beyond standard models, because standard models cannot answer this question.
Right.
And that is why
So we don't know this. So maybe, if you, so it is a good question, good PhD thesis topic for you to try to make a model of the baryogenesis and try to see why baryogenesis happened. So it's an open question. We don't know.
Yeah. So one more question, can there be more Big Bang points? Asked by Krishna Sharkar. What do you mean, Krishna? You have more than one Big Bang points. I mean, in the past, that you have more than one singularity. That is what you mean? Krishna?
Yeah. Okay, so maybe I understand what he is getting at.
Yeah.
So there is no center to the universe. He is maybe asking where the big point happened. Whether the Big Bang happened at many places or one point. Is that
that is what his question is, possibly what I get, but I don't see him around.
So the answer is that Big Bang happened everywhere. If you take infinite universe, Big Bang is not happening at every point, at one point. At the time of Big Bang also, universe was infinite. So Big Bang just means that the density has become infinite and temperature has become infinite. The universe still remains, the universe does not really go to one point. The universe still remains macroscopic. So Big Bang is happening at there are infinite many points where the Big Bang is happening. It is happening everywhere, in fact. It happened everywhere. So it is a point in time, not in space.
That's more important.
Sir, I have one more question. The answer of this question I am searching from HS first year. During my HS first year time, one of my professors told me that when Big Bang has occurred, then the energy moving which is greater than speed of light are creating mass, and something is giving mass. That something is called God particle. Is it right, sir?
No, nothing is everything in Big Bang as well as now. Everything obeys theory of relativity. So nothing, no physical particle can move faster than light.
Yeah, Shaitam, we can discuss about
During
it
Big
later.
Bang, nothing is moving faster than light. So universe is expanding. So you have to, okay, I think I see what is the, what's the confusion?
Talk
If you look
about
at scale factor, right? So scale factor is a dimensionless dimensionless number. There's no point in giving it units of velocity. So scale factor is changing exponentially fast, but no physical particles do in. So if you have some physical observer, you are in a particular frame during Big Bang, you won't see any particle moving faster than speed of light. And if any particle that we will observe will still obey a special theory of relativity.
Hello.
Yeah.
May I ask a question?
Yeah.
Yeah, Devajit, please.
Okay, fine. Thank you, sir, very much. And now I have a question in cosmic microwave background radiation. That is, you have showed us that cosmic microwave background radiation, it is not actually direction independent. There is a slight deviation in all directions, but we get a 2.7 Kelvin radiation. In
Yes.
that case, actually, we can find actually a frame of reference from which that makes we can make that thing, we see that thing direction independent. So there is actually a frame we can find the velocity of that frame from calculation, and that velocity looks like an absolute velocity. Is it actually violates the logical background of special theory of relativity?
No, nothing is violating special theory of relativity. So we're talking about the dipole anisotropy.
Yeah,
Like one side the CMB is hotter, one side is colder, and that tells you that there is particular frame. So you can boost our, you can have put your satellite on a rocket and boost it so that it cancels exactly that dipole. So then it will only see the uniform CMB, it will not see any dipole. It will see some small fluctuations, and that is fine. It is not violating any special theory of relativity. And in fact, any point in space, you can find this frame. So this is our background frame. So it exists every point in space-time, and it's not violating anything.
Okay. So with respect to which we actually measuring that velocity, that is actually.
No, so that is known as CMB frame. So the frame you get when you boost your velocity, so all frames are equivalent, right? So in principle, most observations you can do in any frame.
Okay.
So CMB anisotropy will also look almost same in that frame. So nothing will be, you can do your experiment in any frame and you should get the same results.
Exactly.
Just boosted by this Lorentz transformation.
Sir, I have a doubt.
Yes.
If I hold a stone weighing approximately 1 kilo, why doesn't it blow off into free energy?
So say that again.
If I
Why
hold,
is the mass not getting converted into energy?
yes, sir, that's the question.
Well, so first of all, if you have only matter, it cannot really go into energy, right? So you have lots of conserved charges which exist. So for example, so you can first, before you ask the question of a rock, you can ask why electron does not decay to photon. Right? By energy, you mean some particle, right? There is no such thing as hypothetical. So energy is still some particle. Right? When you say energy, it is either motion of particles, there is kinetic energy and heat energy and mechanical energy. It is motion of particles, microscopic motion, right? And photons have energy, they are pure energy, they are massless particles. So any energy is a particle. There's no energy that exists without any particle. The question to ask is, why does one particle does not decay into another particle? And the answer is that because there are lots of conservation laws which will be violated. So for electron, you have conservation of charge, conservation of lepton number. And this conserved quantities prevent for electron to decay into a photon, which is a neutral particle and does not have a lepton.
Sir, but ultimately it's It's confined in this universe now, sir. It cannot escape. So it is
Yes.
confined. Yeah, anyhow we convert it, it remains the same now, sir.
Yes, but a
Whether it
standard model of particle physics, it tells you that there are lots of conserved quantities which cannot be violated. And that is the reason for things to be stable, right? So you can ask also the question, for example, why does Earth not fall into the sun, right? There is a gravity between them. Can you answer me this question? Let me ask
yes,
you
sir.
this question. Why does Earth not fall into sun?
Because of its tangential motion that's keeping it revolving around it. Because
Yes,
if Earth had stopped, it would have fallen. But because
yes,
Earth is moving, its tangential motion is keeping it
yes.
falling slowly, but not suddenly.
Yeah, so you are right. But there is a conservation law which is preventing this. So what is that? It's the conservation of angular momentum. That is the deeper reason why Earth does not fall into sun. So Earth falls into sun, energy will be conserved. The potential energy will be converted into kinetic energy, and there will be no problem there. But angular momentum will be violated. So angular conservation of angular momentum, which keeps Earth going around the sun. If you take away some angular momentum out of the Earth, and Earth will actually, the orbit will shrink.
Okay,
So,
sir, I got it.
so same
Okay,
way,
yeah,
conservation
you can.
which prevent the particles. Okay, yeah.
Yeah. So you possibly can go through more material and get it clarified. For today, I would like to stop because the speaker
Yeah,
will be tired by now because
yeah.
possibly he is tired. And then we are already almost 1 hour past our schedule. So I think we'll stop here. And from organizers, I have also lost my connection in the time being. So I would like to thank the speaker, Dr. Khatri, for really discussing the physics of CMB. So that this is one point where the students also are really confused at some point of time that what information we exactly are deriving from CMB, why CMB is so important. So I thank you for this and for also being able to be with us today on this occasion when we are celebrating our Silver Jubilee for the department. And I would like to thank the participants for being here today. And tomorrow we will resume back exactly at 4 o'clock. So the second day series of lectures. So please be there on time. And I would like to request Dr. Rishi, if possible, tomorrow the ending session, concluding session, I hope it will be at 7:30, but not at 8:30. So if possible, I think you have some engagement on Tuesday evening, you told me. So in case it is possible, please be there. Otherwise, if you are busy, we understand.
Okay,
So
yeah, I will try to be there.
Yeah. So participants, especially Shumit, was requesting that he wants to have some discussion. So he can write to him, I guess.
Yeah,
So there should not be any.
you are welcome to write to
Yeah.
me if you have.
Yeah. So they can directly write to you if they have some real question. And I see that Shravati Didi is there since beginning. I don't know. She is. Yeah. So tomorrow we have 3 lectures. First is of Professor Navamandal, second Professor Serpico, and the third one is of Professor Shravati. So I hope that evening will be as enjoyable as it was today. And I thank you all and wish you a good night. Thank you.
Thank
Okay,
you.
good night.
I really enjoyed all
Thank you,
the
sir.
lectures.
Yeah, you were there throughout the lectures. I could see it.
I really enjoyed.
Yeah. So thank you. So we are eager to hear from you tomorrow. And today it was really nice to, have, light thrown on different aspects of the standard model and beyond. And I seriously wanted cosmology to be in, and Dr. Khatri did that part, and really it went well. So I thank all the participants and the speaker, and I stop here for today. Tomorrow we will start again at 4. Please be there, because without participants, for whom we will be doing, arranging the event. Okay. So I'm stopping here today. Thank you.
Thank
Okay,
you.
thank you. Good night.
Okay, bye.
Good
Thank you,
night.
sir.
Thank you all. Bye for today.